Hello, everyone. In this video, we're going to talk about section 14.4, which is all about tangent planes. So we're continuing to develop the idea of derivatives for these multivariable functions. So remember, we're considering f, a function from Rn to R, and we're usually going to be working with R2 to R. Okay. But for a second, let's go ahead and step back to the case that we're most used to, this a function of a single real variable f from R to R. And let's think about derivatives for a second. So remember that for a function like this, what is f prime? What does my first derivative give me? Right? Okay, so if this white line is my function and that green line is a tangent line at tangent at this point in particular. Okay, f prime of A would give me the slope of the tangent line at that point. Okay, so it's the slope of the tangent line, right? And then I could, consider that as that derivative as a function on its own. I plug in any x to my derivative, and it's going to give me the slope of the tangent line at that point x. Okay. So we can think of our derivatives as the slopes of our tangent lines. And that's roughly, the slope of the tangent line is roughly the rate of change of that function at that point, right? If I consider this tangent line, okay, at the point A, okay, and it's got slope, let's say 2, well, that means, at that point, that rate of change of my function is about 2, meaning if I go over by a little bit of x, I should go up by 2 times x vertically, okay, in my function value. Okay. But what about the tangent line itself? And how can we think about that tangent line? So let's look at that picture again. Okay. So let's consider this tangent line, this green tangent line. Okay. So at my point, at my x value A, I go up to my curve and I look at that tangent line. And let's see, this point A, comma, f of A, that's on my tangent line, right? This point is on my tangent line and it's on my curve. And how can we think of that tangent line? Okay, it's got a slope which is equal to the derivative, right? The slope m is equal to that f prime of A, that derivative at A. Okay, so the slope is our derivative, but really, that tangent line is it's a nice approximation to our function, at least in the area around A, okay? So the way the textbook tells you to deal with this, or think about this, is kind of like, think about, let's say we kind of drew a box around this area, like just in this close area to our, where our tangent line and our curve kind of meet. And let's kind of really zoom in on that. Okay, so imagine that this box over here is the zoomed in version of that. Okay. So I'd have a very gentle, change in my curve, right? And then my tangent line would be very similar to this curve. It's tangent, it's just touching right there, okay? And then going off. So when we zoom in, we see that there's not, if we get close enough, there's not much difference between my tangent curve, my tangent line, and my function. And that's really what a tangent line is. It's like saying, okay, our tangent line is kind of an approximation to our function in a small area. So we can think of these tangent lines as approximations to our functions. And the more, the farther away we get from this point, the worse our approximation is, right? Like if I was trying to use this tangent line to approximate my function at some point, B over here. Maybe at that point B, my tangent line is like way up here. and my function is way down here, right? So that's not a great approximation. But if I stay in this little neighborhood of A, okay, well, it is a pretty good approximation. Now, it might seem like it's kind of limited, right? That approximation, it's only good in that little area, but it has the added benefit of being that tangent line is really simple compared to our function, right? Maybe this function f of x is really complicated. It has some really complicated equation, but this tangent line, this green line, it's just a line. So the equation for that would be really simple. It's just the equation of some line, y equals mx plus b essentially. So very easy to write. So we have this trade-off. Okay, maybe it's not a great approximation. Maybe it's only useful in a small neighborhood, but at least it's really simple. And you'll if you work with like numerical math, and using computer systems, things like that, there's a lot of these linear approximations and things like splines and I forget the other names for them, but essentially you're constructing like linear approximations to functions. And a lot of numerical math is done that way. So it's very useful. Okay. Going back to this line, okay, we said this line, our tangent line is an approximation of the function. And we talked, okay, the equation of that line is going to be really simple. What is the equation of that line? Okay, let's look at that real quick, because that's going to give us some insight into this topic of approximation. Okay, well, we know the slope of that line is what? The slope of that line is, let's say I'm considering, I want to in particular consider the tangent line at x equals a. So I'm considering, if I go back to this example here and erase all my extra stuff. Okay. I'm considering my tangent line at this point A. Okay, so this green line here. Okay. What is the equation of that line? Well, we know its slope is going to be f prime of A, right? Because my derivative gives me the slopes of my tangent lines. So my derivative at A is going to give me the slope of that tangent line. Okay. So this is the line's slope. And then if we have one point on the line, we can do point slope form, right? Well, okay, we said this point here, A comma f of A, that point is both on my curve f of x and on my tangent line. Okay, so this point is on my line. Okay, with those two pieces of information, I can write the equation of my line using point slope form. Remember, that's like y minus y1 equals mx minus x1, okay, where that m is the slope and the x1, y1 is my point on the line. Okay. So I've just plugged in my values here. Okay. And if I rearrange that, I see that I can, I'm just going to move this f of a over to the other side. I can say y is equal to f of a plus f prime of a times x minus a. Okay. So this is the equation of the line. Okay. Now, what if I want to approximate my function f of x with that line? So I want to plug in like an x over here, and I want to get an approximation to this function value here using this line. Okay. So basically, what I want to do is I want to plug x in to the equation of my line. Okay. So let's just replace y with f of x, okay? And now we don't have an equal sign, right? It's just an approximation. So we have f of x is about equal to f of a plus f prime of a times x minus a. Okay. So we have this approximation here. All right. So another way you might be confused by this x minus a or something like that, f prime of a times x minus a. Another way to think about that is like, we're saying, okay, our function value f of x, we're going to start at f of a, and then we have a slope of our tangent line, right, f prime of a, and then we're multiplying by some distance. So it's like slope or rate of change times a change in the x coordinate. That should give us like some total change, right? And then we're adding to it our starting point. So it's like starting point plus the total change should give us about our function value, our f of x. Okay. So we've rearranged the equation of our line, and we've kind of developed this approximation to our function f. And we could actually be more specific if we wanted, right here, we don't have an equal sign, right? We have this kind of squiggly equal sign. That means it's about equal. We could actually be more specific and say, okay, well, f of x is going to be equal to that line plus some error term, okay? And what we usually say is that this error term is going to go to 0 the closer we get to our starting point, okay? That's what this notation means. And this might seem, maybe you talked about this in Calc 1. I know it's been a while, and if you guys, let's see, some of you guys are coming in with Calc from high school and all that, and some of you probably took it with Dr. Mikuzinski at UCF, and maybe some of you took it at Valencia, something like that. So I realize that some of you may not have seen this before, but this is really what the derivative is all about. If we take the derivative of some function, okay, if we start with f of x, yeah, f prime of x is the slope of the tangent line, but built into this idea of a differentiable function is this idea that we can make a linear approximation to our function, and that involves the derivative for sure. But really, when we're saying something's differentiable, it's kind of like what we're saying is we can make one of these linear approximations to our function. We can approximate our function with a linear function. And in this case, when we have f, a function of a single variable, f r to r, that linear function is just a line. It's, it kind of sounds like what it is. So this idea of differentiable it's when you hear differentiable, I want you to get into the habit of thinking, okay, there's like a linear approximation to my function. Okay. Now this idea is very straightforward for the functions of a single variable, right? The derivative exists, and then we see we can make this tangent line, and it all works out nicely. Now things get a bit more complicated for multivariable functions. Okay, but we're going to try and develop a similar idea for the multivariable functions. And again, we're going to run into some problems when we start, thinking about things coming from different directions, just like with limits and continuity and the partial derivatives and all that. Okay. So let's consider a multivariable function, and for the sake of simplicity, let's consider a function of two variables. Okay, f from R2 to R. Now this is this type of function. Let's just assume it's differentiable. Remember, these derivatives aren't always going to exist, but let's assume this is a very nice function and it's got derivatives in all directions. Okay, so something like this could have lots of derivatives, right? We talked about partial derivatives last time, so it could have derivatives in the direction of x going this way. Maybe I should do a different color. How about yellow? Okay, so we have directions, partial derivative in the direction of x, or a partial derivative in the direction of y, and really you can have derivatives in all the directions in between too. So it could really have an infinite number of derivatives. In the previous section, we were really only concerned with derivatives in those major directions like x and y. But we're not limited to those. We'll talk more about that in the next section. But the point is we got a bunch of derivatives, and really what I was drawing a second ago, that wasn't the derivatives. These yellow lines aren't the derivatives, right? I'm kind of drawing like tangent lines. So we have not just a bunch of derivatives in a bunch of directions. We have these tangent lines all pointing in maybe different directions, right? And we want to use these tangent lines to kind of approximate our function somehow, get a linear approximation to our function. That's kind of where we're headed. But you know, which tangent line do we use, if any? There's, as I just was drawing a second ago, maybe there's an infinite number of tangent lines. Okay, so which one should we use, if any of them? Okay. So, reiterating some of what I was just discussing, we have these partial derivatives in the direction of x and y, et cetera, et cetera. Now, maybe we can't, you know, maybe there's not one tangent line that's going to be a good approximation for our function. That doesn't really make sense, right? You know, how can I approximate this, you know, this object? This is kind of like a mountain, right? How can I approximate a mountain with a single line? But maybe I could approximate it with something, you know, of higher dimension. Is there some object, some tangent object I can make from my function? And the answer is yes, sometimes. You know, we can't always make one of these tangent objects, one of these linear approximations, but if our function's nicely behaved or, you know, structured in a nice way, yeah, we can make one of these tangent things. Okay. And in R2, when I have a function from R2 to R, that object that I'm going to make, that tangent thing, it's going to end up being a tangent plane. Okay, so when I'm working in this case, I'm not going to have a tangent line, right? What, you know, if I take if a line is what I have for one dimension, what should I have for two dimensions? You know, two-dimensional version of what, like a line, I guess. No, not really. I shouldn't say it's the two-dimensional version, but if I kind of take a line and add one dimension, what does that give me? It gives me a plane, right? Okay. So maybe what I should be looking for here is a tangent plane. Okay, so what would that look like? Let's say like I'm at the kind of crest of my hill, and you know, maybe I got tangent lines going in all these directions, and all of these tangent lines are connected, or you know, contained in a single plane, a single tangent plane. Okay, that's kind of just touching my mountaintop. So if I kind of looked at my mountain from the side, you know, maybe I have this tangent plane. Okay, so if I was looking at my plane from the side, it would maybe just look like a line, but you know, it's a plane. Okay. So maybe I have this tangent plane. Let's see, maybe just kind of barely touching my mountain at that point there. All right, if you can picture that. Okay, so maybe that's the object I'm looking for. And I'll spoil it for you. That is what we're looking for. Okay. Now, I just said that, okay, this plane contains all these tangent lines in my directions, like that have to do with my partial derivatives for x and y, etc. So can I use that information to find my tangent plane? So recall how we found equations of planes in section 12.5, I believe. One of the ways, and we could find the equation of a plane, is if we were given two vectors in a plane, contained inside a plane, and a point in the plane. So what did we do? We took the cross product of those two vectors, and that gave us a third vector that was normal to the plane. And then, let's see, what did I do? I had my normal vector, right? And then I kind of have this general point, x, y, z. And then I subtract from that the point I know is on my plane, xo, yo, zo, okay? And my normal vector is going to be normal to whatever vector this is. So it's going to be equal to 0, right? And then I could just rearrange that, might play with my equation a little bit. I can condense these into one vector, etc. And then I can turn, instead of writing in vector notation, I could split it all up and write it in just kind of the standard notation for a plane. Okay, so that's what we're going to do. The question is, what are the two vectors I'm going to start with? Okay, what two vectors am I going to start with? Well, if I have a function from Rn to R, these two vectors are going to be related to my partial derivatives. And I'll explain how that works in this equation, okay, in this example. And then I'm going to give you a nice formula, okay? Once we've seen how it works, I'm going to give you a nice formula. Okay, so let's try and find the equation of the tangent plane for this multivariable function at the point 1, 1, 3. Okay. All right, so there's a couple things we need to do. The first thing we need to do is find these two vectors. And where'd I go? Don't look at this stuff. Okay. The first thing I need to do is find these two vectors that I'm going to use to find my normal vector. Okay. So what makes sense for those vectors to be? Okay. So going back up to the kind of this picture of this general tangent plane I drew. Okay. I'm claiming that this tangent plane, what does it contain? Okay. Let's say there's this white line is the tangent line pointing in the x direction. Okay. What should that vector be? Okay. That should be just like in my function of a single variable. I think about the single variable, the tangent line, right? That's kind of what we're dealing with here. We're kind of restricting ourselves to just this x direction. And so we're kind of thinking of this as like a slice of our bigger function, and that kind of gives us a function of a single variable. Okay. All right. So what would this line be? It's like it's the equation of our tangent line. It's got the slope of our derivative, right? Its slope is our derivative, m equals f prime of x. And what does that mean? It means like, okay, what is the slope? It's like saying I'm moving. Slope is rise over run, right? So if I move 1 unit in the x direction, I'm going to be moving up by f prime of x, right, in the y direction, in the vertical direction. Okay. And then we have a similar idea for this vector in a larger space. Okay, think about this tangent, this white tangent line, tangent to our curve. Okay, it should have a slope, and that slope should be related to our partial derivative in the x direction, right? So what does it make sense to be? It's like saying, okay, I'm going to move 1 unit in the x direction, and then what's going to happen to my functional value, my z value? I should be moving vertically by f prime of x, right? So for instance, let's say this surface is some function of f of x and y, and I find its derivative in the x direction at this point here is -2. Okay, so then what would my vector, my tangent vector right there be? It's like saying, okay, I'm going to move 1 unit in the x direction, and I'm going to move -2 units in the z direction. Okay, so that's how I find my vectors. my tangent vectors. Okay, so they're closely related to these partial derivatives. So the first thing I need to do is find my partial derivatives. Okay, so back to our actual example. What's my partial derivative of f with respect to x? Okay, that's just 4x. Okay, and then when I'm at the point 1, 1, 3, my x coordinate is 1. So in particular, 4 at that point 1, 1, 3. What's my partial derivative with respect to y? Okay, that's 2y. And again, I'm at this point 1, 1, 3 where my y coordinate is 1. So I expect my partial derivative at that point with respect to y to be equal to 2. Okay. So that means my tangent vectors should be like 1, 0, 4, meaning, okay, at this point, if I move 1 unit in the x direction, I'm going to be moving up by 4 units in the z direction, roughly. Okay. So we'll call that, how about we call that V1. Okay. And then V2, what would that be? What would that vector be? Well, we could do 0, 1, 2. That means, okay, if I move 1 unit in the y direction, I'd be moving up 2 units in the z direction. Okay. So these are my 2 vectors. Now to find my tangent vector, excuse me, my normal vector for my plane, how can I find my normal vector? Well, I take the cross product of these two. Okay. So I take my cross product. Let's see, I do my I, J, K, 1, 0, 4, 0, 1, 2. Okay. And what do we get? We get -4, -2, 1. Okay, so that's our normal vector. All right, and now let's see, we have our normal vector and we have our 1 point on the plane, right? So I can use that information to write the equation of my tangent plane. Okay. So in vector notation, I know it's going to be n x, let's see, x, y, z minus x, o, y, o, z, o equals 0. Okay, so let's see, what's my normal vector? -4, -2, 1. And then I do what? X minus xo, xo is 1. Y minus yo, yo is 1. Z minus 0, zo, zo is 3. So that should be my vector equation, right? And I can split this up if I want to write in kind of my standard form. So this would become -4 times x minus 1 minus 2, y minus 1 plus 1 times z minus 3 equals 0. And then last thing I could do, what you'll commonly see is to get z, the z, z minus zo by itself on one side of the equation and then everything else on the other side. Okay. So maybe the standard form to write this for our tangent plane would be this. Okay. Now note what's going on. First of all, we have our point. These are the coordinates on the point on our plane, right? And then what are these right here? Well, this is the fx, and this is my f sub y. Okay. And so we've seen how it works, how we derive this, and then now we can just get, like, for future use, now that we've seen how it works, we can just use a nice little shortcut. If I have a function z equals fxy, and I want to find the equation of its tangent plane at this point p xo yo zo, I can just use this formula. I'm going to find my partial derivatives, f sub x, f sub y, okay, at this point. And then my equation just becomes z minus zo equals partial derivative of x at that point times x minus xo, partial derivative with respect to y at that point, times y minus yo. Okay. So a nice quick formula for equation of a tangent plane. Now, that's the equation of the tangent plane. Now let's think about what the tangent plane actually means. Okay, similar to the tangent line and derivatives in the single variable case, this tangent plane is a linear approximation to our function. And there's a lot of good pictures in the textbook. So check out the textbook and let's see if we can do that together real quick. Okay, hopefully you can see my textbook now, my ebook, which you all have access to as well. Now, Z, and this is actually, figure 2 is actually the example we were just working on, whose equation of the tangent plane we just derived. Okay, so let's look at figure 2. Now, the leftmost figure, leftmost square of this figure, that it's kind of the zoomed out version of what we're doing. So that kind of parabolic surface, that's the surface, that's the graph of our multivariable function z equals 2x squared plus y squared. And then that flat plane, well, that's our tangent plane. Now, what I'm saying is that just like with the tangent lines for the single variable case, that tangent plane is kind of an approximation to this parabolic surface. And maybe if we're just looking at the leftmost square, that approximation doesn't look very good. But then the middle square, that's the same figures, just zoomed in a lot. And now, okay, yeah, there's still a little bit of difference. We can see that my parabolic surface thing still got more curvature than my plane, right? But the difference isn't as noticeable when I'm zoomed in. And then if I move to my rightmost figure where I'm zoomed in a bunch, they're almost right on top of each other. So the closer I get, the more zoomed in I get, the closer I get to that 0.113, the better my approximation is. And that's just how linear approximations work in general. The closer we get to our starting point, the point we're approximating around, the better our approximation gets. And really, that's how we can think of the derivative, certainly in the single variable case, and then we're developing that same idea for the multivariable case. Okay. So now let's move back to the iPad. Okay. So I'm saying that this tangent plane is a linear approximation to our function. And maybe that term linear is kind of throwing you because you say, hey, now we have planes. Why are you calling it linear? Doesn't linear mean line? Well, and linear, if you think back to the last lecture video I did, I believe, linear was one of those terms we talked about, and maybe I told you guys to go look it up on your own. Maybe you did, maybe you didn't. Okay, when we say something, an equation is linear, that doesn't necessarily mean it's just a line. Okay, what the definition of a linear equation is there are equations like these where I have, I have my variables x, y, maybe z. Where were we? Oh, here we are. Okay, so I have my variables, my independent variables. Okay, or not even independent, but I just have my variables x and y. Okay. If I'm only multiplying those variables by constants and then adding everything together, I call that a linear equation. Okay. So this is a linear equation in two variables. Okay, and what is this? And if I'm working in R2, this is just the equation of a line. Okay, so a linear equation gives me a line in R2. Okay, what about in R3? Okay, well, this is still a linear equation, right? I have my three variables, x, y, and z, and I'm just multiplying them by constants, a, b, and c. Okay. So an example, an example in R3, maybe 4x plus 2y minus 3z equals 0. Okay, I have my variables, okay, multiplied by constants. But in 3 dimensions, my linear equation doesn't give me a line, it gives me a plane, right? And then we can have linear equations in more than 3 variables. Here I've written down a linear equation in 5 variables. So the x1, x2, x3, x4, x5, those are all variables. And then a1, a2, a3, a4, a5, those are all constants. Okay, so this is still a linear equation. And the object it gives me, we would call it a hyperplane. Basically a plane in more than 3 dimensions. All right, so that's what these linear equations are. Now we're turning to the idea of the linear approximation. Okay, so the tangent plane, it's the equation of the tangent plane. It's a linear equation. This tangent plane, it's a linear object. Okay. Now, if let's look at the equation of that tangent plane. Okay, in general, the equation of the tangent plane would be, I could write that as z minus z sub 0 equals partial derivative with respect to x times x minus x sub 0, partial derivative with respect to y times y minus y sub 0. Okay, so that's an equation of my tangent plane. And then let's just rearrange it a little bit. Let's get z by itself on one side and then everything else on the other. Okay, so I have z0, which is just a constant. I have, okay, my f sub x, and when I evaluated at the point x0, y0, it's going to be a constant. Okay, and then I got a variable in here. This is going to be a constant. That's going to be a variable. So essentially what I have here, this is a linear equation, right, in 3 variables. And I'm saying that my tangent plane is an approximation of my function. So, okay, this is the equation of my tangent plane. And I can say f of x, y, is going to be approximately equal to the right side of that equation. Okay. The only thing I would change is, okay, what is z sub 0? Well, if z is equal to f x, y, then z sub 0 is equal to f xo y. Right? So I have this linear approximation here. My function values fxy can be approximated by my tangent plane. Okay, so previously we said that these tangent objects, this tangent plane, when we're working in R2, do they always exist? Well, not necessarily. They exist sometimes when our function f is nice and well behaved. So what do I mean by that? What are some conditions for having this tangent plane? And what's the problem? Why don't we always have it? So going back to a single variable case, okay, f from R to R, okay. Things are a lot simpler here, right? If the derivative exists, the tangent line exists. Okay, so if I have some function f, I find f prime, that's going to be the slope of my tangent line. And I can always use that f prime to find the equation of my tangent line. Okay. What's the problem when I move into higher dimensions? it's this idea that, you know, I don't have just one tangent line anymore, okay? As soon as I move into that extra dimension, that FR2 to R, okay? You know, now I have a surface, okay? And maybe I have a bunch of tangent lines all at this point. You know, how can I guarantee that all of these different tangent lines all fit into some nice plane? You know, maybe most of them fit into this nice plane, but then one of them kind of goes off on its own, you know, pointing at a funny angle or something. So how can I guarantee that I can capture all these tangent lines in a single tangent plane? That's really, you know, that's kind of difficult, right? So even if these partial derivatives fx and fy exist, you know, we might not have a single nice tangent plane. Okay? And in fact, we can have partial derivatives and our function f might not even be continuous, which sounds weird, right? Because in a single variable case, f r to r, if f prime exists, we know that f is continuous, okay? And there is a similar result for Rn, but we need more than just these partial derivatives. If we have the partial derivatives f sub x, f sub y, that's not enough to guarantee our function's even continuous. And so it's certainly not enough to guarantee that some tangent plane exists. And the problem really, again, comes from the this idea that we have so many directions to consider, not just, you know, this single variable case where, you know, I can only approach, you know, a point A. I can only approach it from the positive or negative side. You know, now we have all these weird ways to approach. If you think back to the section 14, what was it, 14.2, when we talked about limits and continuity. So this example here is really a classic example of how our intuition from the single variable case might steer us wrong. This is a function. Its partial derivatives exist, but this function is not even continuous. And there's a nice. This is straight from the textbook. There's some nice figures to go along with this example. Okay. You know, as an exercise, you know, try and compute fx, the partial derivative with respect to x, partial derivative with respect to y, and then consider these partial derivatives close to this origin, you know, close to 0, 0. Okay. You should get that these partial derivatives are they go to 0 in the neighborhood of this this origin point. So these partial derivatives are you know, fx. What is fx at 0, 0? That's equal to the limit. It's a limit, right, of fx plus hy minus fx y over h as h goes to 0. This limit exists. Okay, even if my function is not necessarily continuous at 0, 0, this limit might exist. Okay, and if we calculate our partial derivatives and kind of look at our limits closely, we see that the limits of these things, these limits equal 0. So our partial derivatives are equal to 0 at the origin. Okay. But does that jive with the idea of a linear approximation, right? If I try to use these partial derivatives to make a linear approximation, what would it end up with? I would say fxy, kind of using my tangent plane linear approximation. Okay, I would say fxy is about equal to f00 plus f sub x, okay, so 0. Okay, so I get this very kind of simple approximation that fxy is approximately 0 in a neighborhood around very close to my origin. Okay, and that might sound reasonable at first. Okay, but go back up to your original function. Okay. Okay, and don't even think about the derivatives. Think about this function. Okay, what happens along the line x equals y? Okay, so if I have my 3D plane, if I kind of approach the origin along this line here, well, if x equals y, then my function is essentially x squared over x squared plus x squared. So x squared over 2x squared. So it's equal to 1/2. So all along this line, my function is equal to 1/2. But my linear approximation is saying, well, in a close area, it should be about 0. But it's always equal to 1/2 along this this line. So that linear approximation doesn't really work for this function, does it? It kind of breaks down. And the problem is, one of the problems is that my derivatives aren't continuous. There's more going on here than just that, but we can solve a lot of problems if our partial derivatives are continuous. Okay. So what we're seeing here is that partial derivatives, just the existence of partial derivatives is not enough to guarantee a linear approximation of a tangent plane that can approximate our function. Now, there's a couple ways, we need a new idea of differentiability of this linear approximation. So we need something a bit stronger than just partial derivatives. Okay, so there's a couple ways to define this, and I'll kind of give you mine first, but what we should probably stick with is kind of what the book says. Okay, mine, and it might be more simple, but don't devote too much time to this. Let's say I have a function from R2 to R. I'm going to say it's differentiable at the point a comma b if this limit exists. What is this limit? It's f of x plus h, y plus j, minus f of x, y over hj. Okay, so what's going on here? On top, I have an absolute value. Okay, right? fxy, or whatever I'm plugging into my function, this is just going to give me a number, right? And then I'm subtracting a number. Okay, so this is a number minus a number, and I'm taking the absolute value. Okay, so this top is an absolute value of a number. What is this bottom? Well, this hj, that's a vector, right? So this bottom is the magnitude of vector, which again, okay, once I take the magnitude, it just becomes a number, right? So what is this saying? This is kind of a way of dealing with the problem of direction of approach. We're saying that this limit, no matter what h and j are, no matter what path I'm approaching my point a comma b, and in fact, let's change these to a, b. So no matter what path I'm approaching AB along, this limit exists. So this is kind of like saying it doesn't matter what direction you're approaching from. It doesn't matter if you're approaching from the x direction or the y direction. If this limit exists no matter what, then we say our function is differentiable. And this is saying a lot. This is saying more than just partial derivatives exist. So this is a lot stronger. Now let's see how the book phrases it. Okay, so let's say you have a function z equals f of x, y. Okay, we're going to say it's differentiable at the point a comma b. If delta z can be expressed in this form, or delta z, think of delta z as a small change in z. Okay. So if you can write delta z as the partial derivative of f with respect to x times a small change in x plus partial with respect to y times small change in y, plus these error terms, where the error terms are getting smaller and smaller as we get closer and closer to, as our changes in x and y go closer to 0. Okay, okay. If all that is satisfied, then we say our function is differentiable. And really, these two things are equivalent. If you went higher in math, you know, this is the form you would see. This is kind of the more mathematically rigorous form, but if this is easier to understand for you, that's fine, and that's obviously what the book considers the default. Okay. So that's the definition of differentiability. Okay, that's what it means for a function of multiple variables to be differentiable. Okay, and let's talk about the difference between differentiable versus partial derivatives. Okay. These are kind of related concepts, but this is saying more. Okay. So if we say partial derivatives exist, okay, that means the derivatives in the directions fx, fy, whatever. And if we're in two variables, it's just fxy, fx, fy. If we're in three variables, you know, we would have a z as well, and we can have more. Okay. So if we say partial derivatives exist, all we're saying is fx, fy, fz exist. If we say a function's differentiable, we're saying a lot more. We're saying, okay, yeah, those things exist, those derivatives exist, but also, let's say I have this surface here, okay? So if partial derivatives exist at that point, yeah, these derivatives exist. But if my function's differentiable, then that means like all the derivatives in between also exist, okay? So this is a lot stronger. But that's just a definition. Now, we can see that, all right, if our function is differentiable, then we are going to have this kind of nice linear approximation. Again, this is kind of a linear approximation. So if our multivariable function is differentiable, yeah, we're going to have a nice linear approximation. So the next question we're going to ask is, all right, when is a function actually differentiable? When is that limit going to exist? Well, that's a very complicated question, and it's something you devote not insignificant amount of time to in grad school. So it's not, you know, it's not something you can just read a couple pages on in Calc 3 and have mastered. It's a pretty deep question, but one result we have that is going to be sufficient for most of our, probably all of our class. Okay, if those partial derivatives exist and are continuous at our point, then f is going to be differentiable at that point. Okay, so before we had, you know, we saw an example where things didn't work out. The partial derivatives existed, but they weren't continuous. Okay. So what I'm saying is, if we have a bit more, if the partials exist and are continuous, then our function f is going to be differentiable, meaning we'll be able to take the derivatives in any direction and, you know, kind of make this tangent plane out of them all, okay? So if we have partial derivatives exist and are continuous, okay, f is going to be differentiable. We're going to have a tangent plane, which is the same as having a linear approximation. Okay. All right, so that's really the highlight of that last piece, this theorem here. That's really powerful, and it's going to satisfy most of our requirements for the course. So a lot of this course is finding linearizations. So if you see a question that asks to find the linearization, you're essentially finding the equation of the tangent plane. We can do more examples of that in our class meeting. I want to just briefly touch on differentials before I wrap up the video. All right, what is a differential? It's a notation that's closely related to the derivatives. And really, they're used to indicate small changes in values in relation to one another. So, for example, if we had a function of a single variable where I had y is equal to f of x, then this differential notation is, you know, this is what we would call this differential notation. dy, okay, what is this saying? It's like saying a small change in y. Okay. And then we're saying that dy is equal to f prime of x dx. All right, so what does that mean? It means a small change in y is, you know, we can describe our small change in y as a change in x times what is, so dx is my change in x, right? So maybe I should do this in the other order. What's my f prime of x? F prime is like my change in y in response to change in x. And then I'm multiplying by a small change in x. So that makes sense, right? If I want to find my change in y, I can take my rate of change of y with response to change in x, and I can just multiply that by the total change in x, and that should give me my total change in y. So that's for a single variable. Now for multivariable functions, it's a little bit more complicated, but it's pretty straightforward. Okay. So if I have z, let's say I have z is equal to function of x and y. Okay. Now, I can't necessarily write change in z as just a change in x times its derivative, and I can't necessarily do the same thing for y, right? Because, all right, well, maybe my change in x depends on both, or excuse me, my change in z depends on both change in x and change in y. Okay. So I have this idea of the total differential, meaning, all right, my change in x, or excuse me, my change in z is going to be my rate of change. What is f of x? You can think of that as change in z with respect to change in x. Okay. All right, then you're multiplying by change in x. And then you're adding the same thing, but for y. Okay, so change in z with respect to change in y, so blah, 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 times change in y. And if I add these two changes together, I should get my total change in z. Okay? So fairly straightforward idea. It's confusing notation, but just think of it as these small changes, and we really can think of this as, again, a linear approximation. Essentially what we're saying is, you know, look at this total differential. It's essentially just kind of the equation of our tangent plane, really. Okay. Or instead of z minus z0, you know, I have really just dz on this side. So let's see an example of how this would work. Let's first calculate the total differential for this problem here. Okay, what would my dz be? Well, we know from the formula it's f prime of x dx, or maybe delta x is how it's in your textbook, but should be fine. Okay, times, and I shouldn't have f prime of x. I should have f sub x, right? Of xy plus f sub y of xy dy. Okay. So I need to calculate my partial derivatives. So what's my partial derivative with respect to x? What's my partial derivative with respect to y? Okay. So that should be my total differential. Now this is example 4 from the book, and this is part A. We've kind of calculated our total differential. And then part B goes on to say, okay, if x changes from 2 to 2.05 and y changes from 3 to 2.96, they actually ask you to compare delta z and d. All right. What we've solved for here, or what we have here, is going to give us our dz. Okay. So what is delta z? Okay. This is our differential. Delta, and this is an approximation, right? This is just an approximation. Delta z would be the exact change in z. Okay. So to find delta z, we would actually have to find, z at, let's see, 2, 3, our original point, and then we would find z at 2.05, 2.96, and then delta z would be equal to exactly z2 minus z1. So we get to find exactly what that change in z is. But this differential gives us an approximation to our change in z, and that's going to be a lot easier to find. Okay, so how do I find this dz? Okay, I have my derivatives here, right? My partial derivatives. So what are those partial derivatives at my starting point of 2, 3? Okay, basically I'm just going to plug 2 and 3 in for my x and y. Okay. So I have 13 here. And then what's this partial derivative? It'll be what? 6 minus 6, so 0. Now, what's my dx? I know what my dx is, right? It's my change in x. So my x value goes from 2 to 2.05. So that's an increase of 0.05. And then this is going to be, this term here is just going to be 0. Okay. So my dz should be equal to 13 times 0.05, and yeah, that works out. It's going to give us 0.65. So my dz is 0.65. So that means as I go from 2.3 to 2.05, 2.96, my z value should change by about 0.65. Okay. All right, that wraps up this section. More to come.